just about time to start. Welcome to this afternoon session on Nobody Puts Java in a Container. And probably this title is the first thing I would like to clarify a bit. Who recognizes where this quote is coming from, or what the original quote is? Who recognizes it now? Even more people? That's Nobody Puts Baby in a Corner from Dirty Dancing, of course. But what this talk actually is about, it's about putting Java in a container. And it's not about that nobody should put Java in a container, but it's about telling you what you should know before putting Java in one of those containers. And I hope this aligns with your expectations here. Maybe a short raise of hand. How many of you have worked with Docker or some container technology before? Almost all of you. That's great. How many of you have looked at like how it works deep down with cgroups, namespaces, and everything? Fewer raise of hands. I will have some slides which might be boring for those people who just raised their hands, but please bear with me so we can connect it later back to Java. How many of you are using Java or some Jre-based technology? Again, almost all of us. So this is a great intersection, and we'll talk exactly about how we can bring Jre together with Docker or some other container technology. Who am I? I'm a distributed systems engineer at Mesosphere, and that's a fancy term of saying I'm programming C++ on the Apache Mesos project, which is like an open source cluster resource manager, which is used by Twitter, Airbnb, Apple to run like their large clusters. So, as being said, I'm more on the C++ side of programming, so why do I necessarily care about Java? And I promise this is the only DCOS slide I will have. So what we are working on is Mesosphere. It's called DCOS, the Data Center Operating System. And that's basically, it's built around this Apache Mesos project I mentioned earlier. And this enables you to run both your containers, your microservices, your big data analytics, Spark, Kafka, Cassandra, Elastic, and so on, all on like one common platform together with monitoring, security, and so on and so on. So I usually care because a lot of our users, open source users, so all of this is open source, and a lot of also our customers, they're running Java applications on this application. On this platform. And naturally, if they're using microservices, they're also using some kind of containers. So we actually have a lot of users who are running some kind of containers based Jre applications on this platform. So let's dive into the first part of the name, containers. So containers, they have this really cool promise, write once, run anywhere. So, and this is what I really like about it. I can actually start here on my laptop, develop an application, package it into some kind of container image, and then it's very easy to deploy and run this container image anywhere else. This promise, write once, run anywhere, we will see where that kind of breaks, or where we have to be aware of what anywhere means. But this is kind of like the promise, and this is, I believe, also the real value we get out of using containers, that it actually becomes shippable, and we have a much easier time of testing it locally and then rolling it out to some remote production server. But actually, we heard that promise before with Java. It's also write once, run anywhere. And also, if we consider it, Java is also some kind of container because it's a Java virtual machine. So it also already containerizes my application. And as said, we will see how these two can actually interact and work together in this talk. First of all, what is like the big difference to virtual machines versus a container? The big difference is that actually in a container, I'm running everything on the same host operating system. So what container underneath are, they are basically just process groups on some kind of Linux kernel usually. And those process groups, they're isolated from each other. So all of this, it's running on the same kernel, whereas if I'm using virtual machines, where we see that still a lot of users are migrating from over to this container world, I have a different level of isolation. Because here, actually I have for each of those application stacks, I have an own guest operating system. And this operating system it behaves pretty much similar to as we would be used from a normal operating system. And this is basically different here. We just have, in the container world, we just have one operating system on which all applications are running. This actually has several implications. First of all, we have weaker isolation. So as it's all running on the same kernel, if I manage to crash the kernel, some kernel bug or whatever, in the container world, I'll actually bring down all applications running on the same kernel, on the same machine. If I'm doing the same in the virtual machine picture, I will only bring down that virtual machine because that kernel is targeted to that virtual machine. On the other hand, as it's just a process group, actually those containers, they're running near native CPU and I/O speed because it's just one process group in a kernel. And also the start times, it's the same, pretty much the same start time as I would have for any process. So we're somewhere in like the sub-second range, whereas with virtual machines, even with KVM, I usually spend like a few seconds on starting up a virtual machine. And overall, of course, I also have much less storage overhead. I have much less memory overhead because I'm not like running an own operating system for each of those application stacks. So I'm actually saving a lot of resources and I'm gaining flexibility as I'm faster in deploying those. But on the other hand, it's a trade-off that I actually have weaker isolation guarantees. So if I, for example, if I would run, I have my multi-tenancy platform and I'm running Coke and Pepsi workload on the same cluster, I would actually make sure that they always end up on different machines in order to have proper isolation in between them and not just isolate them with containers. So if I really have strong isolation requirements, I would make sure that it's actually running on different kernels, either VMs or different machines. So to just really symbolize that, if we just do a simple docker run nginx, and we actually on the host operating system look at all the processes running, we can see all the processes running. So we see everything from the host operating system perspective because it's a process group on the same kernel. So we already use containers, the word container, quite a lot, but actually we can mean different things with containers. So first of all, even if we're just sticking to this Docker world, when people are saying I'm using Docker, it can actually mean different things. It can mean I'm using the Docker runtime, so or formerly Docker daemon. It can mean I'm using some Docker images, so like Docker Hub, I'm pulling the Ubuntu image from there, which probably most of us have done already. Or it can actually mean I'm referring to a running container instance, because this is like once I have typed my Docker run nginx, then I have one instance of this container running. So already if we are sticking into this Docker world, we already have some ambiguity what we actually mean by container. If we are going beyond the container runtime, there are actually many other runtimes. So for example, in DCOS, we have something called Universal Container Runtime, which can also run Docker images, but which doesn't actually need a Docker image, as we'll see in just a second, to run that. If we have used Kubernetes, there's another standard, so they actually have an abstraction, the runtime interface, container runtime interface, and then they have their own implementation for that. So there are actually like many different implementations to run containers, because what containers in the end is, it's just this isolated process group, which we saw in the image before. So just as one example, that we don't actually need a Docker image to start up a container, something we can do in DCOS or actually Marathon is we can have the simple app definition, and you don't even, it's not crucial that you understand all of it, but as you can see, we don't specify a container image. We only specify which URIs, so which artifacts we actually need to run our class, to run this application. And with Java, this could be like my app.jar, and it can be like a JRE I'm pulling from some kind of server. And then actually on the fly, I can still construct this process group running with those artifacts, and I don't first have to package all of this into a single Docker container and then run this Docker container. So this is just to symbolize that there are actually multiple ways of spinning up such container. It's not, I don't always need an image to do that. I can also create this image on the fly by just fetching those artifacts here. Then let's talk about isolation, because isolation, this is like this crucial property I also want from my containers. First property we just saw is package all those artifacts into like some deployable form. And the second thing I would like to get out of my container environment is actually isolation. So if we look down, it's actually what's used underneath are all kernel features. And this is also why, for example, Docker images, they're not tied to the Docker daemon, because underneath most of those tools, they'll actually do the same. They will utilize cgroups, control groups, and namespaces to isolate those process groups from each other. And then there are, for example, different container stacks, so the lib container or other tools to actually address that. But what comes down underneath are those two fields here, the control groups and namespaces. The namespaces, what they actually do, they provide isolated views for each process group. So if I'm a process group, I'm this Nginx container we just started, I want to see my own process IDs. I don't want to see any process IDs of any other containers. I want to see my own, potentially my own networking stack. I want to see my own host name. I want to manage my own users without actually affecting those users running on like the same kernel underneath on the host operating system. So this basically from inside a container, namespaces, they give me the illusion as if I would be a virtual machine, and I can control all of this for my own container without affecting anyone else. So the other side is then actually I also need to kind of isolate and control from a resource perspective. So otherwise a container might jump in and actually consume all the CPU resources. It might consume all memory. So it might actually affect all the other containers running on the same platform. And that's where those control groups are coming in. They're actually there to control resources, and they're kind of first of all accounting for the resources, so they're checking how many resources are used by this one process group, and then they can also enforce constraints. For example, this process group is only supposed to use 2 GB of memory. As soon as they're using more, we will kill them. And one really cool feature, and this is something you should also keep in mind when, for example, implementing something yourself, is the freezer process group. The freezer process group basically freezes your process group, and so you'll receive no CPU shares anymore, so nothing will move. And where could I, for example, use that? Imagine you want to kill a process group by using the process ID. Usually we would kill type like kill -9, whatever ID, and then this process group would be gone, or this process would be gone. The problem when doing that in some kind of orchestrated fashion, what I would do, imagine like a loop. I first get the process ID of that container, and the next command I will fire is actually kill -9 this container. Unfortunately, what could have happened in the meantime, that process from which I just pulled the process ID has finished, and now actually another process has started, and once I issue the kill -9, I will actually kill this random process which is just by chance started up in the same time. So if I start by freezing this process group, I can be sure that it will still be referenceable under this same process ID, because we know nothing can have happened in between, because the process group has received no CPU shares. So this is like a really neat feature to implement orchestration systems dealing with such kind of containers. Control groups. So control groups, and right now when I'm talking about control groups, I'm talking about version 1. There's also version 2, which is drastically different actually in the way, for example, this tree is set up. But for the point of this discussion, it's actually sufficient to look at version 1 here. So as everything in Linux, it's just a tree, and I can also do like an ls on it, on like sysfs cgroups. This is where it's usually mounted in most systems, and I can just have like this view. And what I'll see is actually there will be different subsystems. So there will be a memory subsystem, a CPU subsystem, and each of them, they have their own hierarchy. And here on the right, we can see like an example of this hierarchy. So for example, here I have structured my CPU hierarchy into batch processing frameworks and into real-time processing frameworks or processes. And then I have a further nesting under batch. I have like my Bitcoin miner, and I have my Hadoop framework. And then what we see, these numbers underneath, those are the actual process IDs of the processes running in there. In each of those subsystems, in each of those subsystem hierarchies, each process ID can only occur once. So it has to be really assigned to one of those. And but it can occur in multiple hierarchies. So for example, 52 occurs up there, and it occurs here in the CPU one, because we want to isolate it for each of the subsystems available. And then what I can do, once I have this hierarchy, I can actually assign constraints. So I can, for example, say in the memory one, my databases, they should have a maximum of 4 gigabytes of RAM on that machine, for example. And then the shared subtree underneath will only have 4 gigabytes available. And this is what the control group would actually enforce. If we look at, if we stick to this memory example, this limit we just said, we can actually enforce it in different ways. So we can have hard limits or soft limits with memory. Soft limit means we only get a warning, and they tell us, hey, don't use more memory, but nothing will actually happen. The default way, for example, how Docker implements it, or how Docker uses it, actually, it's not really implemented, is to say we have hard limits. So those hard limits are actually enforced, meaning you can visualize it as kind of like a polling process. So there's a process which always checks like how much memory is my all processes under my databases using. So 1008 and 524, how much memory are they using? And it's kind of like a continuous loop polling that. As soon as it sees that it's using more memory than those 4 gigabytes we assign to it, it will actually just kill it. And this is already some different from what we might be used as a Java programmer, where we actually get like a nice out-of-memory error, and we could actually handle that. In that case, our processes will simply be killed. And I can set those limits. I can set them for all kinds of memory, so physical, kernel, total memory, and so on and so on. All right, C groups. So for CPU, it's a little different. I have, again, 2 kind of different ways of doing things. First of all, if I simply want to use it for accounting, imagine I'm billing my customers or my groups inside my company based on how many CPU shares they use. I can also do simple accounting with that, but I can also, again, set limitations. And there are 2 ways of doing that. The first one is CPU shares, and the second one is CPU sets. First of all, CPU shares, it's basically a priority weighting across all cores. And when you start a process without specifying that explicitly, it's going to be 1024. And then it just depends on like how much do you assign to your task. So if we look at this example where we have C groups A and C groups B, and we assign a share, this can be like any number, like 768 to C group 8. And then we have C group B, which we assign 256. And assuming there's nothing else running on that node, on that kernel, the kernel will assign the CPU shares, the CPU cycles. 75% of the CPU cycles will go to group A, and 25 will go to group B. And you see, this highly depends on how many tasks are running. If we would start a third C group, this would again change like the overall limit. So it's kind of just a priority weighting, who has more priority than someone else. If we actually want to enforce hard limits, because just imagine cgroup B being the only one running on that machine. It would actually could consume 100% of the CPU shares. And that could have some interference with other stuff. So if I really want to make sure that it's not using more than one CPU, or like 1/4 of a CPU shares, I can use something called CFS, which is the completely fair scheduler in the Linux kernel for hard limits. Again, those slides will be available later on. Just click on that link to follow up with details. But this is like a way of enforcing like hard limits, and kind of avoids this greedy approach that someone can actually consume more than he potentially could. And if we're using Docker, it's simply by specifying the -c flag. This corresponds to CPU shares. CPU sets are different. CPU sets, they actually allow me to pin those process groups to specific CPUs. So, for example, down here, Docker run CPU set 046. This would say this process group, this container, will own the cores 1, 5, and 7. And they'll be pre-assigned to this container. Usually, I would not advise to use that, and also the standard container schedulers, they don't use it, simply because you're already statically partitioning your cluster. There's also a paper by Google who basically say you should only in very rare circumstances use CPU sets, and those rare circumstances are if you experience heavy bouncing between two CPUs, then you might actually want to bind it to a specific one, or if you have like a really deep or variant NUMA architecture, so non-uniform memory access, where you want to group all CPUs together who can access like the same memory region in an efficient manner. So those are like typical use cases when I would use CPU sets. Namespaces. Namespaces, as mentioned earlier, they provide each of those containers with its own view of the overall system. So typical namespaces are process IDs, network, mount. I don't want to see the mounts of another container. Users, each container should be able to have its own users. And also, each process by default will be in one of those namespaces. So even if we create like a standard process, it's going to end up in like a standard namespace. And if we just look at the process ID namespace, so if I start up a container with its own process ID namespace, it also can only see processes in the same PID namespace. And as we can see here in the second most left column, I also, in this container, I have a process ID 1, which is kind of like the core, the parent process ID. And this is unique to each container. And when I would look from the host operating system, I could still see like the same process, but it would have a different process ID, because this is process ID 1 is only valid inside the container, inside the process group. All right, that's enough about containers. Let's talk about Java. Again, Java, similar as Docker, if we say Java, we can actually mean different things. So we either talk about the Java language, we can talk about the Java specification, or as we do in this case, we can look at the Java runtime. And first of all, if I start any Jre, what is the memory impact? So what I usually do, I often set like a heap space, a max heap space, a min heap space. But there's actually much more memory impact. So first of all, the Jre also needs some memory impact. Then there's the perm/now meta space. My JIT bytecode compiler also needs some kind of memory to run. If I use JNI, it also uses non-heap memory. Neo, so the I/O, it's so fast because it uses non-heap memory. And also, if I use threading, I'm also using non-heap memory. So just like a typical rule of thumb, but that heavily depends on your application. for setting, for example, those container limits is to consider something like 2 times the heap space. But as said, this really varies for your application, and there the best advice is actually to monitor that. To monitor how much is your application actually using, that you get a feeling for to how much memory you should set that. Because this can also vary over the lifetime of an application. Typical, the Jre, when starting up, it consumes a lot of CPU. It consumes also some more memory to start up. Spring Boot apps even more. But then over the later runtime of a job, it can actually be less. So there, I would do some profiling and actually monitoring of how much memory is actually used, that I can set the limits specific to my application. One thing, so recently they switched from the perm to meta space, and this is basically space around. So for example, it's used by the class loaders and so non-heap memory. And before, the perm space was actually included in the heap memory. With the new meta space, which is like the similar thing, it's outside of this heap space, so it's also not constrained by that by the Jre anymore, and actually it lives in the native memory space. What that means is that, in contrast to what happened before, if I had a class loader leak and I would just spin up too many classes and waste my perm space, at some point I would hit my heap limit and it would just crash. Now as we move to meta space, what will actually happen is I can take up as much resources as potentially the machine is offering me. And so there we already see that it can actually make sense to run the Jre constrained in a container, because it will avoid the meta space to take over the entire native memory on that machine. So now let's talk a little bit, switch from memory to CPU, and let's talk about the Jre Default Initialization. So there's an asterisk, and we'll see how that varies between different Java versions on one of the coming slides. But when the Jre starts up, and I don't override those explicitly, what the Jre will do, it will look at how many cores, how many processors do I have available on this machine. And then it will set the default number of JIT compiler threads, the hotspot thresholds, the default number of threads for garbage collection, the default number of threads in the common fork join pool, and so on, based on this core number. And there we can already guess where some trouble might be if we run that in a container. And we'll see those trouble once we bring now the container world and the Java world together. And imagine we follow this promise of Docker. I deploy my Jre app. I develop it here on my MacBook. Has 4 cores. Everything is running great. It's running in Docker. I started. Everything cool. Now I actually move into production. And in production, I'm starting 10 instances of this Docker container, and it's running on a 32-core box. What will happen as we have this default initialization? It will actually start 10 times 32 cores seen by each Jre. So this entire system of 10 JVM containers will believe there's 320 cores available. And so what they'll do, each of the Jres will start 32 threads for the common fork join pool. Each of the Jres will start 32 threads for the garbage collection, and so on and so on. So as each of them believes it has like the full box available, it will start 32 threads as kind of like the default core. And as you can imagine, this, especially if we have some constraints saying, for example, that each of those containers is only restricted to 1 CPU, this will soon end up in thrashing. So what often happens if I'm really running on a large box and I start a lot of threads, Java, the Jre will only switch between threads and will not get to do any meaningful work. And let's just look at, again, where this is coming from. So this is similar to our image from before. It's actually coming as the Jre will look at the host operating system for metrics. And so before Java 8 or U131, it would actually just report that number. And so also use that number. Because it's looking at, like, if you care about details, it's looking at the sysconfig parameter, and that's just set for the entire machine. In JDK9, it's actually looking at the scat get affinity, which is a bit better because that already accounts for CPU sets. So if I'm using CPU sets in Java 9, I will actually only see in this example 3 CPUs being available, and also therefore my default thread count will be 3. So there I'm actually fine. But if I'm running this pre-Java 9, so Java 7 for example, I'll still see the overall number of processors being on that box, and again starts the overall number of garbage collection threads, for example. With CPU shares, it actually doesn't matter. With CPU shares, it's the same with Java 9 and Java 10. I'll always see the total number of cores available on that machine. How about memory? Memory is actually worse because for memory, we're actually looking at, imagine if you're looking at proc mem info from within your container. This is a file in your Linux system which doesn't get rewritten for your container, right? So always what will read out of this mem info proc file, it will always be whatever is available on the overall machine. Similar with other memory-related techniques. So with memory, it's even worse. It's kind of really difficult to constrain your application to that. Java 9. Java 9 has this promise. So for example, now it supports Docker, CPU, and memory limits. Let's just look at what that actually means. For CPU, that means that we are considering CPU sets because we are looking at the scat get affinity. And the scat get affinity is actually aware of CPU sets. But as we, in the standard, if we would just run Docker in the standard configuration, -C, we would still only get CPU shares, so we would still run into this problem. With memory, we have 2 flags, and if we enable them, so first you have to unlock the experimental VM options, and then you can use cgroup memory limit for heap. And what then the Jre will do, it will initialize its heap space based on the memory you have assigned to the memory cgroup limit. As we've seen before on the earlier slides, there's actually not just the heap space available. There's the Neo, there's the Jre. So that's actually not sufficient. But it's a step in the right direction, and I'm less likely to have my container killed because of memory exceptions. So what is kind of the conclusion of all of this? I should be aware of what's happening, and most importantly, I should be aware probably of this picture, that the JVM is actually accessing the underlying host operating system, and I can control most of that by setting flags specifically to my environment. So whenever starting up my app, I should set those parameters as garbage collection threads and so on, heap space, based on my actual environment and based on my cgroups, based on my container environment. So just to summarize, containers, they're actually really cool because they don't hide the underlying hardware from us. This makes us fast, this makes us efficient, because I don't have the overhead of running like a VM in between. On the other hand, it's also a bad thing as it doesn't hide all those nitty-gritty details, because I say you can only use 2 CPUs. This is not hidden from the container, from the process group. So it's bad for VM technologies because they are not aware of the C groups actually isolating them and not the underlying host operating system isolating them. That's it. Thank you very much for listening.